Video, I will give a brief review about the paper Miracle, Causally Aware Imputation via Learning Missing Data Mechanisms. Regarding the background, the main problem this paper attempts to solve, and related learning algorithm. In machine learning, missing data is very common and an inevitable byproduct of data collecting process. However, it needs to be handled properly for a successful learning. Data can be missed on purpose by human error or malfunction of data collecting system. There have been several schemes proposed to deal with missing data, but those approaches fail to grasp the underlying missing data mechanism. This paper is especially interested in imputation method with respect to causality. Missingness in the missingness data set could create a spurious correlation between the variables, and the imputation of missing data inferencing on observed data could be inaccurate. In a complete data set, such missingness node in the figure would not exist, and thus each variable will be independent to each other. Moreover, missing data creates a shift between the available missing data set and the target complete data set. Considering that, the learning problem here can be thought of as an extrapolation, where learning with missing data set to inference on the complete data set. With this interpretation, imputation on a given data y from observed variable x can be formulated as a problem of optimization over the set of distribution p arising from interventions on missingness indicators as expressed in expression 1. Imputation with causality, as expressed in the second expression, will be then closely related to this optimization problem, with an uncertainty set Q defined as a distribution arising from interventions on observed variables and indicators. The authors expect that minimizing the right-hand side of expression 2 would lead to correcting spurious correlation introduced by distribution shift due to missing data. In this paper, the authors propose a novel imputation method called Miracle, which is a framework for imputation that works on any kind of existing imputation method. Given initially imputed data set, Miracle iteratively refines the imputation by learning missing graph, a causal model which will be formulated later in the slides, and by regularizing the imputation function in a way that it is consistent with the causal model. This paper takes structural causal model as the basic semantic framework. To briefly introduce and help understanding of the SEM, I have attached the definition on the left side and stated Miracle's version of semantic framework on the right side. The authors define SEM-M as 5-tuple, where X is a vector of endogenous variable, U is a vector of exogenous variable, R is the vector of missingness indicator, where each element Rj can take the value of 1 if corresponding endogenous variable is observed or 0 otherwise. F represents a function which outputs X or R, given the parents and exogenous variables of X and R. Lastly, P stands for distribution of variables. And the distribution of exogenous variables is the actual cause of the randomness of the model. Through function f, the SEM-M can induce the endogenous distribution Px. With the SEM structure, missingness mechanism can be represented in missingness graph, or M-graph, which is a directed acyclic graph, or a DAG. To be more precise with missingness mechanism, there are 3 types of missing mechanism, namely missing completely at random, or MCAR, missing at random, MAR, or missing not at random, MNAR, and they are depicted in the figure. MCAR is where probability of missing is same for all data cases. MCAR occurs in a situation where, for example, collecting information about lunch menu from a group of people. Respondents would decide to answer, and respondents decide to answer depending on a coin flip. MAR is where probability of missing is the same within the same data cases. An example would be a survey on military experience. Female respondents in the population are very much likely to have no response. If missing mechanism does not fall into either MCAR or MAR, then such case would be MNAR. In this case, the probability of missing varies due to unknown reasons. The author states 4 assumptions listed to guarantee the learning of missingness graph. First assumption, missingness indicators are not causes holds if the missingness indicator R is generated after the variable values are assigned. The second assumption, causal efficiency, states that exogenous variable U are mutually independent. That is to say that all common parents of endogenous variable are included in X. Third assumption states that there is no self-masking missingness, which is depicted in the last slide. And the third assumption assumes that the self-masking missingness does not exist in the missingness graph. Otherwise, missingness of self-masked variable cannot be learned. The last assumption states that the root node of the graph is observed because imputation of missing variables needs to be done depending on their parents. With these assumptions in place, IRACLE can provide improved imputation by leveraging the causal structure underlying the data generation process. And here's the overview of IRACLE. IRACLE corrects the shift in the distribution due to missing data by searching the causal solutions and refining imputation methods using a penalty on the induced causal structure. To be more precise, the goal is to compute the imputed data x tilde, which is defined in the slide. Here, the circle with the dot represents the element-wise product of matrices, and x hat is an estimate of the complete data matrix. To estimate the data, the authors propose an imputation network, which is defined as a function that takes an initially imputed data x tilde, 0, and outputs a refined imputation x hat and an estimation of the probabilities of features xij being missing. The network indeed consists of 2 subnetworks, namely fimp and fmiss, with length d and ds respectively, where d represents the number of elements in each data, and ds represent the number of missing data. Each subnetwork is responsible for imputing the unobserved data and estimating the probabilities of missingness. The 2 subnetworks share a hidden layer, but have separate input and output layer. Each subnetwork is then defined as a chain of layers as written on the slide, where W represents for the weight matrix. Phi in the expression is the ELU activation function, and sigma in the fmiss is the sigmoid function. Then the network is optimized with respect to 3 objectives, namely reconstruction loss, causal regularizer, and moment regularizer. Reconstruction loss is optimized to train the network to correctly reconstruct each feature from the observed data. Causal regularizer is used to ensure that the dependencies defined by the network correspond to the DAG. Lastly, moment regularizer leverages a set of moment constraints in the missingness pattern to improve imputation. In the reconstruction loss, the first loss term is for reconstructing the observed features, and the second loss term is for estimating the probabilities of missingness. In causal regularizer, bold B represents adjacency matrix, and the graph induced by learning the network is acyclic if and only if the regularizer holds. Moment regularizer is indeed used to enforce the equality given at the bottom. And the given equality holds for MAR and MCR. Missingness patterns. With these loss and regularizer, IRACLE iteratively refines the value by optimizing the loss L given at the bottom. where beta 1 and 2 are hyperparameters to be tuned to decide the strength of each regularizer. And that was the end of the brief introduction. And here's what I'm planning to do for the final presentation. First, I'm planning to analyze the experiment result by the authors and then reproduce the experimental result with the code shared by the authors. And lastly, I would like to compare the author's result to my result and see what's different. Thank you.